In this video series, we'll be focusing on the multi-chassis link aggregation technology, both from an architectural point of view and a configuration point of view. We'll use a configuration sequence to look into the architecture. This implementation on ArubaOS CX is the same for both the 8400 and the 8320 switch series. First module, we'll take a look at MCLAG. We'll describe what it is for, and some details on the differences with other technologies. First of all, MCLAG, it stands for Multi-Chassis Link Aggregation Group. It refers to a technology that allows you to build layer 2 distributed link aggregation groups across two chassis. In other words, it allows you to create MCLAGs or distributed lags with ports on two different devices. Some ports on the device on the left here, the 8400 on the left, and some ports on the 8400 on the right. It is supported on ArubaOS CX, and it's exactly the same technology for the 8400 and the 8320. So everything we say and present during these videos is exactly the same for both platforms. However, it is important to notice that this is not the same as VSF, IRF, or VSS. These three technologies and other similar technologies that are available in the market are stacking technologies, or can be also described as device aggregation technologies. These technologies allow you to take two devices, and in some cases up to 4 devices, and create a single virtual device with a single control plane and a single management plane, and every function is distributed. In other words, you have two devices that behave as a single chassis with a centralized control, centralized management, and distributed forwarding. That is not what we have here in MCLAG. In MCLAG, we have independent routing, independent management, independent multicast routing, and we have independent layer 3 interfaces, but we share layer 2 link aggregation groups. What is the goal of MCLAG? The goal of MCLAG is to eliminate spanning tree from the links between the layer 2 access switches and the aggregation blocks. An aggregation block is usually a pair of two 8400s or 8320 switches that are connected to one or more access switches or access stacks. These access switches or access devices can also be Aruba controllers. In a case like the one that we're seeing here, if the link between the two chassis at the top is a layer 2 link, and because the two links going down to the access layer switch or access layer device are also layer 2, then we have a loop. So we need some technology to get rid of that loop. In the past, that technology used to be STP, or it's multi-VLAN implementations, MSTP or RPVST. In our case, with MCLAG, our goal is to replace these technologies with something based on link aggregation that allows us to get active paths and also have much better response times in case of failure. So what we have here is a pair of devices that can share link aggregation groups and have port members on the same aggregation groups across the two chassis, and that connect using these multi-chassis link aggregation groups to connect to third devices. So MCLAG is used to talk both about the technology and a particular link aggregation group with ports on both chassis. An MCLAG pair is a pair of 8400s or a pair of 8320 switches that share MCLAGs. An MCLAG peer, so each one of the chassis in that pair is a peer of the other chassis. So these two peers form the MCLAG pair. There's also an MCLAG partner or a lag partner. And we're using the word partner because that is the word that the IEEE uses in the link aggregation standard. So the lag partner is a neighbor that has its own link aggregation group connected to these ports that are distributed across the MCLAG pair, forming an MCLAG. In terms of interoperability, MCLAG has been tested successfully against Aruba switches, in other words, switches based on ArubaOS switch operating system, Commodore-based switches, Cisco Catalyst switches, and Aruba 7000 and 7200 mobility controllers, both running ArubaOS 6 and ArubaOS 8. In all the cases, the lags on the access device were configured using LACP active mode. Based on our testing and on the variety of devices that we are presenting here, we can assume with confidence that any device that supports the IEEE or complies with the IEEE standard for link aggregation will be able to connect successfully to MCLAG across a pair of 8400s or 8320 switches. In the next video, we will record and we'll talk about the control plane, a first part of the control plane, and in particular, we're going to focus on the ISL, the inter-switch link of the MCLAG technology. Let's now take a look at the control plane of MCLAG in ArubaOS CX. In this part, we will focus mostly on the ISL function, and later on, we'll take a second look at the control plane in terms of the keep alive function. So the MCLAG control plane is a set of functions that run on each one of the chassis of an MCLAG pair. They talk to each other across something called the ISL or the inter-switch link. The control plane is used to verify configuration consistency, enable the creation of MCLAGs, and it maintains synchronization in terms of LACP information, etc. This is why LACP needs to be active with MCLAGs. You will see that in the future. But the most important thing here is that the MCLAG control plane shares information about the partners connected to the different MCLAG ports. The ISL is the inter-switch link function, and it runs on top of a physical link between the two switches, and that physical link can be a single or an aggregated link, and it needs to be a VLAN trunk, so it needs to be layer 2, and it does not need to be dedicated. That link will be used both for data and for control. That's why we say that the ISL is a function and not an actual link. It's a function that runs on top of that link. That's the control plane traffic. And then regular data can also be transmitted from one chassis to the other across the ISL. As part of the MCLAG control plane function, there are some hello packets that are used by each one of the peers to know that the other peer is not only alive, but it's also accessible through the ISL. As a leading practice, we recommend that the uh, ISL is a layer 2 link aggregation group with at least 2 ports. In those ports, if possible, if we are talking about 8400 switches, that these ports are located on different modules. Of course, that is not possible if you have a pair of 8320s. The LACP mode for that ISL is recommended to be active on both chassis. And also in terms of VLANs that we transport across that layer 2 link, all the VLANs that will be transported by any of the MCLAGs in that MCLAG pair need to be transported across the ISL. And that will provide the full connectivity for the MCLAGs. In terms of architecture, the MCLAG control plane uses the ISL, and the ISL allows these two modules on each one of the switches to talk to each other and also to maintain the synchronization of the MCLAGs on both chassis. The ISL configuration is extremely simple. In this case, I'm using the link aggregation group number 128. That is the highest number of any lag. And as we said, it needs to be a layer 2 link, so the no routing command needs to be part of that configuration. And then MCLAG interswitch link is the command that enables both the ISL function across the two chassis or between the two chassis and enables the MCLAG function globally across the two chassis. As we said previously, we need to transport all the VLANs that will be connected to the different access devices across the two or across the ISL. It is important to see that both configurations or the configuration on each one of the chassis for the ISL is exactly the same. So to avoid misconfigurations, it is recommended to cut and paste the configuration to both chassis. So you make sure that all the commands are exactly the same and you can attain 100% consistency across. Then, of course, you have to add ports to those to the link aggregation group that forms the ISL. The ISL has some timers. Here we're referring to two of those timers or intervals. The hello interval is the time that you set between hello packets. So at the beginning of every hello interval, the switches will transmit a hello packet to its peer, and then they will make sure that they receive these hello packets. They will be monitoring the hello packets received. The dead interval is the amount of time that each one of the peers will wait until between hello packets, and if the dead interval is over without having received any hellos, it will determine that either the ISL or the peer are down. In that case, we will see later that there is a mechanism that will allow us to understand if the failure is the ISL itself or it's the peer that has been shut down or that has failed. So by default, the hello interval is 1 second and the ISL dead interval is 3 seconds. So by default, you will wait for 3 missing hellos until you declare your peer to be unreachable. The leading practice is, or the recommendation is, keep the default timer configuration. We haven't seen any reason to change those defaults. In the next chapter, we will analyze multi-chassis link aggregation groups and we'll see how to configure them across the two chassis. So we have already had an overview of MCLAG, the technology, its purpose, and we've also introduced the ISL as part of the MCLAG control plane. Now let's start looking into the multi-chassis link aggregation groups themselves and see how they look like and how we configure them. So a multi-chassis link aggregation group is a layer 2 only distributed link aggregation group, and of course ports are shared or are distributed across two chassis. The LACP mode of any MCLAG is always active because LACP is required, and the LACP uses the hashing options that have been configured globally. So if you haven't changed anything, it will use the default configuration for hashing, and that means that the hashing key is a combination of the IP source and destination addresses. In the case of packets that are not IP packets or still do not have a source and destination IP addresses, MAC addresses will be used instead for hashing. It is not a layer 3 link aggregation group, and in fact, when we get to the point in which we look at the way to configure a multi-chassis link aggregation group, you will notice that as soon as you say that your lag interface is multi-chassis, that group is configured as layer 2, and you cannot change that. Leading practice or recommendation, use multi-chassis link aggregation groups to connect to layer 2 devices only. Do not connect layer 3 devices at the other end of the MCLAGs. And these devices need to support LACP, and LACP is recommended to be in active mode on that third device. Continuing with our architecture, you'll see that besides the ISL that we have configured, now we have a link aggregation group that has been configured as multi-chassis, in that has member ports on both chassis, on both devices. At the other end of that group of links, you'll find a single device or a stack of devices, and connecting a single link aggregation group up to these two aggregation devices. From a configuration point of view, you can see that here we're creating the link aggregation group number 10 as multi-chassis. As soon as you add the multi-chassis word after the interface lag 10 command, the link aggregation group is put into layer 2 mode only, and you cannot be changed to layer 3. As with the ISL, you need to define the VLANs that will be transported over this link aggregation group. Remember, if you have different multi-chassis link aggregation groups and you have different VLANs on the different MCLAGs, remember that all the VLANs on every one of the MCLAGs need to be configured on the ISL. Finally, add the interfaces on each one of the chassis to the link aggregation group. One more thing, notice that the configuration for both chassis is exactly the same. And again, the recommendation is to cut and paste on the CLI the configuration to avoid having inconsistencies in the configuration. In the next section, we will analyze another part of the MCLAG solution that is called the active gateway. Now let's take a look at Module 4, and here we will cover the active gateway function that is part of the MCLAG solution. Because you're connecting access devices and through the access devices clients to these two chassis in the aggregation layer, and because your access layer is layer 2, you will have to point your client's default gateway to the respective VLAN interfaces on the or behind the MCLAGs on the two chassis. As we said, these two devices are independent in terms of layer 3, so each VLAN interface will have its own IP address on each one of the chassis, each one of the MCLAG peers. That means that the MCLAG peers are independent from the VLAN interface point of view. There are two hosts in that subnet, if you want to look at it that way. So the question is, how do we get a single default gateway when we have two different routed interfaces or VLAN interfaces pointing towards that client? The active gateway is a function that allows you to have a single virtual IP that is active on both interfaces of that particular VLAN on each one of the chassis. So the active gateway allows you to have an active virtual IP, including its own MAC address, that will respond to ARPs on both MCLAG chassis or MCLAG peers. It is defined at the VLAN interface level, and it includes, as I said before, a MAC address, a virtual MAC. It is not a shared router interface in the sense that the active gateway is not visible by or to, for example, OSPF processes. OSPF processes will only see the real IP address of the VLAN interfaces. So the OSPF process, for example, or BGP process or PIM process, will see both chassis as PIM, OSPF, etc. neighbors, and not as the same device. So, in this sense, we can summarize that by saying that MCLAG does not provide distributed routing. The routing is, or distributed routing interfaces. There is each device is its own routing entity. Why are we using Active Gateway and not VRRP? VRRP by default is a master backup configuration, and it is not useful when you have a link aggregation environment. If we had one of the VLAN interfaces on, let's say, the chassis on the left as the VRRP master and the interface on the chassis on the right side of the pair as the backup, traffic going to the right switch from the client will have to be forwarded to the VRRP master across the ISL, and that is something that is better to avoid. So the active gateway, the first advantage is that it provides this active virtual IP interface. The other advantage of using an active gateway has to do with the future developments of MCLAG. The active gateway uses the same MCLAG control plane, or uses the same control plane as the rest of the MCLAG solution. And that is important because if we want this to evolve, for example, to include layer 3 link aggregation groups in the future, it is important that we have the whole technology as a single with a single control plane instead of having to rely on a second protocol for the IP interfaces. So the active gateway is the solution that we're looking for. It's very simple, and let's look at the architecture. From an architectural point of view, you can think that, for example, if you have a VLAN X that is attached to that or transported by the multi-chassis link aggregation group N, then you'll have VLAN interfaces that are independent on each one of the chassis, but you'll have the active gateway that on top of the individual IP addresses and MAC addresses of the individual VLAN interfaces on each chassis for that VLAN X, you have a third IP address that is common and that will be used as the default gateway for your client in this case. So the active gateway is the key, and you can think of it as something that is shared between both VLAN interfaces. And if we look at the configuration, you'll see that in this case VLAN 10 and VLAN 20 on chassis A, they have their own IP addresses, and that is different from the IP address of the VLAN 10 and VLAN 20 interfaces on chassis B. However, if you look at the active gateway command, you will see that both the IP address and the MAC address that we have to add is the same on both chassis for each VLAN interface. So as we said before, the active gateway is shared and provides a single active IP address and MAC address for the MCLAGs that will transport these VLANs. So with this, we have covered the active gateway. In the next module, we'll get back to the control plane description, and we'll take another function in the control plane called the keep alive. Now let's return to the control plane. There's an additional function in the control plane that is called the keep alive. The keep alive is a control plane mechanism that will be used if one of the peers determines that the other peer is unreachable. That can happen in two cases: if there's a failure in the ISL, or if the other peer is down for any reason. It could be because of a reboot of a software upgrade process or because of a failure. So the keep alive is a layer 3 heartbeat between the two chassis that does not rely on the ISL. So we will be sending these heartbeats between the two chassis using another path. That other path could be a second link between the two chassis, a point-to-point link between the two chassis. It can be on a different VRF, or it could go between the two loopback interfaces, and it could use any routed path between the two chassis, any layer 3 path. The key is that if you're using a point-to-point link, you will get better performance and better recovery time than if you are going from one chassis to the core and back to the other chassis using a routed path across the core. Let's look at the architecture. We're focusing again on the MCLAG control plane, and we had all the control plane functions that we described earlier across the ISL. The keep alive does not use that path, and it is a layer 3 connection between the two MCLAG control plane functions. How does this work? The ISL, suppose that the ISL state has been determined to be down because you have not received hellos during the whole duration of the dead interval. that means that, for example, if you're using the default values, there were 3 hello intervals without receiving a hello. So let's look at the state. If the ISL state is down, but you still have a keep alive running and the keep alive state is still up, that means that it's only the ISL that is down, but the peer is still up. In that case, the action that the MCLAG technology will take is that one of the peers will shut down all the ports that are part of MCLAGs. The reason for that is that if the ISL is down, we don't want to have duplicated paths without synchronization. On the other hand, if both the ISL state is down and the keep alive state is down, that means that the whole peer is down, so no action needs to be taken, and the switch that determines that both of these states are down will keep forwarding normally across all the MCLAGs, or all its own ports on every single MCLAG. The logic here is that one of the switches will be, the switches in the pair will be determined as the primary role, and the other one will be will have a secondary role. That depends on the priority, and by default the priority is 8. The priority goes between 1 and 16. And if you want to force one of the two switches to become the primary, then you have to take that MCLAG keep alive priority and bring it down to 1. So the one with the lowest priority number will become the primary of the MCLAG pair. So here's another look at the architecture. What happens if the ISL is down but the keep alive is still up? Let's assume that the switch on the right is the switch that has the secondary role, either by having a higher priority number, or if the priority number was the same, randomly this one was selected to be the secondary. And in that case, the ports on that switch that belong to different MCLAGs are shut down. So now the whole traffic is going to go through the switch on the left, or the primary MCLAG peer. So in terms of configuration, if you look at the chassis B here on the right, you'll see that we have lowered the device priority to 1 from its default 8. So chassis B will become the primary chassis. In terms of keep alive, here we're using the loopback interfaces, so any path between the two chassis is going to be selected. Another option is to use a direct layer 3 link between the two chassis and use the IP addresses at each end of that layer 3 link as the peer and source addresses for the keep alive command. As a summary, MCLAG is a multi-chassis link aggregation group, or a distributed link aggregation group across two chassis. It is supported on ArubaOS CX, and everything that we have described is the same for the 8400 and the 8320 switch series. As we said at the beginning, MCLAG does not provide a full stack integration. It is only a layer 2 link aggregation, distribution, synchronization technology, and it adds a layer 3 active gateway address to the VLAN interfaces that are related to these MCLAGs. The rest of the control plane and management planes are independent for each one of the chassis. The other thing that the MCLAG is not is a distributed routing architecture in the sense that routing is, as we said before, independent on each one of the chassis. With that, we conclude this MCLAG architecture video.